This is the lab video report for the Cylinder of Doom lab from Group 4 of Aero 302. This video report covers the test, results, and analysis of the laboratory. So for a quick overview, in the events of this lab, we observed and analyzed how airflow travels over a cylinder. By operating the wind tunnel at different speeds and utilizing fog machine smoke, we were able to capture a large amount of cool flow visualization videos. With these videos, we were able to study the changes in boundary layers, vortex shedding, and other flow quantities. A smoke machine with a nozzle was positioned directly in front of the wind tunnel inlet, and a member of the lab team was positioned on top of the wind tunnel to direct a laser and a floodlight through a ceiling window. The cylinder was surrounded by pressure reading ports, which made it possible for us to also analyze the flow numerically. In terms of objectives, our first objective was to determine the pressure and drag coefficient of the circular cylinder at different air speeds. There were a total of 24 pressure ports around the cylinder which read pressure data. The sixth port was damaged and did not read data, but using the other 23 ports, we could still analyze and visually display the pressure and drag coefficients across the cylinder at different air speeds. Secondly, in this lab, we wanted to explore how Reynolds numbers and surface finish would affect the airflow around the cylinder. By changing the air velocity, we could study the effects of Reynolds number on the flow. In order to evaluate how a rough surface finish might affect flow, we added trip strips made out of sandpaper on the cylinder to trip the boundary layers. Taking data at each speed with and without trip strips, we were able to examine how the boundary layer, vortex shedding, and turbulence changed. Third, we attempted to find explanations for errors and uncertainties within each test. Naturally, we should be concerned about the error that occurs in testing, but by visualizing each test's error, we could potentially reason as to why more error occurs in one test compared to another. Whether error occurs from instrumentation or effects of the airflow, understanding how and why we are uncertain of our measurements is important. And fourth, ultimately, we were looking to gather flow visualization which would have qualitative and quantitative value. Cylinders are tricky beasts, simple in structure but complex in airflow dynamics. Throughout this lab, we took a lot of really cool videos which displayed complicated processes. We will go more in depth soon to explain some of the amazing phenomena occurring in our videos and data. In terms of test conditions, these tests were run at relatively low Reynolds numbers, typically between the orders of 10 to the 4th and 10 to the 6th. This range follows the flow regime such that a cylinder is expected to shed vortices and form a von Karman vortex pattern. The wind tunnel speeds were controlled by setting the wind tunnel drive system to spin at a fixed RPM with the variable frequency drive, or VFD. Data collection would have begun at each fixed RPM. However, due to a malfunction with the data collection software LabVIEW, observations and video were taken of the cylinder and its effect of the air flowing around it. The wind tunnel speed was increased up to 300 RPM and then 550 RPM, where observations and videos were taken as well. This lab required the calculation and analysis of several important coefficients and constants to quantify the flow. The flow across the cylinder was measured in pressure, but was converted into a coefficient of pressure. Pressure readings were also used to calculate the drag coefficient as well. The vortex shedding behavior was quantified as well by calculating the Strouhal number for each test case or solution.
The first set of tests was done at 3 different wind tunnel speeds based on RPM. Low-speed video was taken from the control station side of the wind tunnel to analyze the vortex behavior as well as the separation location. The first set of tests we do are completed without the addition of a trip strip. This first graph displays the coefficient pressure at operating speeds of 0 RPMs to provide base data to compare to. The spike that we see is because one of the ports was broken and did not record data properly. The x-axis is organized by angle starting at the stagnation point of the cylinder and going clockwise about the cylinder, with airflow moving from left to right. At a low speed of 150 RPMs, we can see that vortices are shedding off the back of the cylinder in a turbulent manner. As vortices fluctuate, the air is displaced so the cylinder's boundary layers grow and shrink as well. The airflow seems to separate from the cylinder around the top and bottom points of the cylinder. Our coefficient of pressure graphs for fan speeds of 150 RPMs shows that the flow around our cylinder matches the shape of the theoretical curve roughly. However, the theoretical curve assumes inviscid flow. In reality, the flow detaches from the cylinder. As you can see on our plot, our data becomes a horizontal line near angle 90 or port 6. This is where the airflow detaches from the top of the cylinder. One of the potential reasons for error in our data is because of the turbulent vortex shedding creating differences in pressure data. At the next fan speed of 300 RPMs, we see vortices shedding slightly faster off the back of the cylinder, but still with a large amount of turbulence. The boundary layer seems to be more steady than at 150 RPMs, but the flow still looks like it separates near the top and bottom points of the cylinder. The coefficient of pressure graph for 300 RPMs is very similar to that of 150 RPMs. Our data detaches from the theoretical curve because the airflow separates from the cylinder. At high fan speeds of 550 RPMs, the vortex shedding seems to happen further in back of the cylinder. The boundary layer, subsequently, is higher and more prolonged, but still, flow detaches near the bottom and top points of the cylinder. Our coefficient of pressure graphs for high speed is very similar to the graphs of lower speeds. However, the horizontal section seems to contain less variance and the error bars also look smaller. This could be because of a more consistent flow at higher speeds. By comparing each speed's qualitative and quantitative properties, we can conclude that flow separates near the top and bottom of the cylinder without any trip strip. We can also see that vortex shedding, which is all turbulent in these three tests, is directly related to Reynolds number. We can also conclude that flow is steadier at higher speeds, at least for this set of tests.
Our second set of tests were conducted at the same speed as the first set. However, 2 sandpaper strips were added between ports 8 and 9 and between ports 16 and 17, which are located just in front of the top and bottom surfaces of the cylinder. Upon inspecting the flow visualization performed at the low speed of 150 RPMs, you can clearly see vortices being shed behind the cylinder. However, the boundary layer appears to stay attached for slightly longer, and the vortices appear to form farther away from the cylinder as compared to the test performed at the same speed without the trip strip. The coefficient of pressure graph confirms this relationship, as the curve follows the theoretical curve for slightly longer than it did when there was no trip strip in place. When we look at the flow visualization performed at the medium speed of 300 RPMs, we can see that the separation point is further back again when compared to the same speed without the trip strip. The vortices being shed are harder to see as the flow appears to be more streamlined around the cylinder. The coefficient of pressure graph again confirms this relationship, as we see the curve follow the theoretical curve for much longer than it did without the trip strip. When we look at the flow visualization performed at the high speed and high Reynolds number, we can see that the flow appears to be very streamlined, and the boundary layer appears to stay attached for much longer than it did without the trip strip. As a result, the vortices are very difficult to see, although they are still there. The coefficient of pressure graph here again confirms this relationship, as you can see it follows the theoretical curve for much longer than it did without the trip strip. From our second set of tests, overall, we were able to conclude that both higher Reynolds numbers and the addition of trip strips both delay the separation point of the flow around the cylinder. This delayed separation also reduces the vortex shedding seen behind the cylinder. When the coefficient of pressure graphs for the second set of testing are overlaid on top of one another, we can clearly see that at the lower Reynolds number, the flow separates sooner than it does at the higher Reynolds numbers.
For our overall observations, we noticed when the fan's RPM increased, there was an increase in the frequency of vortex shedding. Additionally, adding the sandpaper trip strips to the top and bottom of the cylinder decreased the frequency of the vortex shedding. When we take a look at these pressure coefficient plots, the right-hand side being the runs with the trip strips affixed and the left-hand side being the ones without the trip strips, we see on the right-hand side that the flow separates at around 120 to 115 degrees, and then again at 250 to 270 degrees, as opposed to the left-hand plot where the flow is separating at about 90 degrees, and then again at about 300 degrees. This increase in separation angle on the right-hand side indicates flow being attached much longer to the cylinder. When we take a look at our drag coefficients, our drag coefficient is higher at the lower Reynolds number, then decreases to a relatively constant value at higher Reynolds number. This trend occurs for both our test conditions with and without the trip strips, but without trip strips, our drag coefficients are a little bit higher on average. This can also be seen in our drag force plots. but our results are really notable when we look at the tabulated format, where runs with the trip strips showed a decrease of drag force by almost half when compared to runs without the trip strips. This trend is noted as well with the coefficient of drag.
When replaying and observing our flow visualization videos, we were able to observe the general area on the cylinder where separation of the flow occurred. In general, it is better to have flow separation occur at a later point along the object being tested rather than at an earlier point, as it will help minimize the size of the vortices as well as overall turbulence coming off the object, in this case a cylinder. When observing the flow visualization data we collected, it was seen that when a higher Reynolds number or higher flow velocity was achieved, the flow in turn stays attached for a longer time and separates at a later point along the cylinder. In addition, when the trip strip is added to the cylinder, it is observed that the separation points are delayed, and this is expected because the turbulence that the trip strip introduces re-energizes the boundary layer, which in turn causes the flow to be capable of staying attached longer. One of the quantities of flow that we also needed to characterize in the cylinder of Doom lab report was the vortex shedding coming off of the cylinder due to turbulent flow. The main mathematical quantity used to describe and characterize the frequency of vortex shedding is known as the Strouhal number. When calculating the Strouhal number, the main quantities in question are F, the frequency of shedding, D, the diameter of the cylinder, and V, the free stream velocity. The figure above shows how the Strouhal number changes due to an increase in Reynolds number. In the graph, the Strouhal number hovers right around a value of 0.2, which is what we should have expected to see with our experiments and observation. Displayed above are the calculated Strouhal numbers at each wind tunnel RPM, both with and without a trip strip on the cylinder. As seen in the table, the numbers are slightly lower than 0.2, with the highest being 0.1833. This is most likely due to the low precision method we used for flow visualization, capture, and analysis. On the next two slides are a comprehensive error table including all the possible sources of error that might have shown up in our experiments and calculation. Most likely the highest possible source of error that we encountered was due to the smoke quality we observed in flow visualization. Unfortunately, we had to resort to the method of slow motion video capture by camera to record our flow visualization. This is because our lab group experienced issues with launching and using the LabVIEW program installed on one of the computers monitoring the wind tunnel. In addition to this, the fact that we did not have port 6 available for data collection on the cylinder was most likely our next highest source of error. This would have resulted in the airflow of an entire section of the cylinder being uncharacterized, thus giving us much less data points than would have been available to us for data analysis.
So in conclusion, after running our tests such that we can calculate our coefficients of drag and pressure at a certain range of Reynolds numbers while taking into account the error in our testing, we've determined that cylinders in general create considerable drag at low Reynolds numbers. And in addition, delays in separation can reduce the pressure differential across an object such as a cylinder in our test, thus reducing drag.